Hello and welcome back to CMOS RF integrated circuits. We were discussing frequency synthesis techniques, so that is what our business was, and we had developed some sort of a fractional synthesizer, fractional N synthesizer, that is what we called it. Today we are going to take a relook and understand where are the spurious frequencies, if at all, right. So, that is what we are going to understand, and then we are going to develop better ways of doing fractional synthesis. Okay. So, that is my plan. Now, just a recap. So, this is what we wanted to do. We wanted to have the phase lock loop, and on the feedback path I wanted to divide by k. K is supposed to be programmable, and I should be allowing k to be not just integers, also fractions. So, this is the basic problem, right. I want k to be a fraction, not an integer, not just an integer. Integer is easy to do, that is what we did in the first shot. We found that my loop bandwidth would be very restricted, and restricted loop bandwidth means I need a better phase noise performance as far as the VCO is concerned. I need to allow for slower settling time, as in longer settling time. So, it will take much longer time to hop from one frequency to another, the synthesizer. So, these are the problems with lower loop bandwidth. I do not like lower loop bandwidth. So, as a result I need to be able to divide by a fraction. So, this was the basic premise of the story. Now, given that this is the basic premise, we developed a way to divide by a fraction. I said let us divide by 2 for 2 cycles, let us divide by 3 for 3 cycles. You could generalize this and say that let us divide by capital N for k cycles, and let us divide by capital N plus 1 for m cycles. But of course, k has to be a multiple of n and m has to be a multiple of n plus 1, that is. But of course, and I said that let us assume that k equal to a times n and m is equal to b times n plus 1. So, k cycles and m cycles. So, the total number of cycles that I am waiting for is k plus m, which means the period, the net period of the whole business is k plus m cycles at the output. So, my fundamental for the spurs will be at this particular frequency. I will get spurious frequencies. This is the net period for those spurious frequencies. So, I will be getting some up pulses, some down pulses, etc. Okay, and they will keep repeating at this frequency. So, this is the fundamental. Okay. And then we figured out that the average period, all right. So, then I figured out that over the duration of the net period is so many clock cycles. Okay. Over the duration of a n plus b n plus 1 clock cycles, the output is going up and down a plus b times, which means that on the average the divided frequency is f out, that is the frequency at the output, times a plus b, it is going up and down a plus b times, over a net period of a n plus b n plus 1 clock cycles. Okay. So, this is my divided frequency, and therefore, I have achieved a division by this particular factor. this is what I have managed to do. Now, what does this mean? Is this number going to be more than n? Has to be more than n, right? This is definitely more than right. So, this is definitely more than n. Is it more than n plus 1? No, it is not more than n plus 1, it is a little less than n plus 1. Right. So, I have managed to divide by something which is more than n less than n plus 1. Okay. And by what fraction is it more than n? By b by a plus b. So, that is why it is called a fractional n synthesizer, all right. So, you are dividing by a little more than capital N, little less than capital N plus 1, but of course, sometimes you are dividing by n, sometimes you are dividing by n plus 1. So, in effect you have got to be, on the average you have got to be dividing by something more than n less than n plus 1, right. So, this is basically the plan. Now, n can be a large number, n can be I do not know, n can be 1000, n can be 100 for example. Okay. You could say for our previous example, what was the example we had chosen? I do not see the example anymore. This is the example that we had chosen. The input reference is at 10 megahertz. I want an output between 900 megahertz and 1.1 gigahertz. So, with a channel raster of 1 megahertz, this was my plan. So, I want to be able to divide by k ranging from 90 to 110 with the first decimal place. So, can this go from 90 to 110 in steps of 0.1? How will you do that? See, n can always be changed. So, the range of n has to be from 90 to 109. Okay. If you want a little more, you can range n from 90 to 110, no problem. What about b and a? I want a plus b to be a number like 10. So, I can have 10 possibilities, a equal to 0, b equal to 10. I really do not need to do that. I could just choose a equal to 10, b equal to 0, it will give me the same thing, same effect, right. I can go for the next higher number. So, I have got these 11 possibilities, one of them is redundant, does not really matter, and that will cover this entire range, and I will get my steps of 0.1. Now, how do you organize this? Before that, a plus b is now equal to 10. What does that mean as far as the net period is concerned? I am calling something the net period. What was the net period? That is going to give me the fundamental frequency for the spurs. Okay. This is the net period, and over here a plus b is restricted to 10, which means that I have got 10 times n plus b times p out. Okay, that is my net period, which means that the fundamental as far as the spurs are concerned, right. So, where are the spurs coming from? The control voltage is having some glitches at a certain frequency. What is the fundamental frequency for that? The fundamental frequency for that is f out divided by 10 times n plus b. What is our division ratio? Our division ratio is n plus b by 10, right. That is our division ratio, a plus b I am saying let it be 10. This is a specific example that we are doing. That is equal to 10 times n plus b by 10. Okay. That is my division ratio, which means that the frequency f ref is equal to 10 n plus b times f out. Right, and just do a little bit of jiggling and you will see that this is what you have got. F ref was 10 megahertz. So, you have got the fundamental for the spurs at precisely 1 megahertz, which so happens to be the same as the fundamental for the spurs in the integer n case. Amazing, right. So, you decided to have a certain channel raster. No matter what you did, whether you did an integer n circuit or whether you made this complicated fractional n circuit, the spurious frequencies are precisely at the channel raster frequency, no other strange frequencies. This is really amazing, and unfortunately this has rather bad consequences for this kind of a fractional n synthesizer. Why? Because the basic premise of building the fractional n synthesizer, why did we build it? Why did we make it so complicated? Divide by n plus 1. We made it so complicated because we wanted larger loop bandwidth. I want a 10 times larger loop bandwidth. So, that is why instead of having the channel raster frequency as 1 megahertz, I made the channel raster frequency equal to 10 megahertz, and instead of dividing by integers, I divided by integer 0.1 decimal place. Right? This was my basic plan. That means that my basic idea was to increase the loop bandwidth by 10 times. Loop bandwidth, let us say it is 1/10 of the reference. So, reference was 1 megahertz, loop bandwidth was 100 kilohertz. So, in the integer n case, reference was 1 megahertz, loop bandwidth 100 kilohertz, spurious frequencies are appearing at 1 megahertz offset from the output, which means that the loop is rejecting significantly the spurious frequencies. They are out of band. Spurious frequencies are at 1 megahertz, 2 megahertz, so on. Loop bandwidth is only 100 kilohertz. So, 1 megahertz, 2 megahertz are getting rejected by 20 dB, right. In our case, in this fractional n case, the new loop bandwidth is 1 megahertz, because that is why I built the fractional n. The spurious frequencies are at 1 megahertz, 2 megahertz and so on, same as before, and therefore, the spurious frequencies are passing right through the loop without any attenuation. It is within the loop bandwidth. Do you see what we are pointing at over here? The problem that we have over here? The problem that we have over here is that fractional n has larger loop bandwidth and the spurious frequencies are within this loop bandwidth. So, they are going to pass right through. The integer n has narrower loop bandwidth, the spurious frequencies are out of band. So, in both cases, the spurious frequencies are appearing precisely at the channel raster frequency, right, spacing between two channels. So, this is a big problem. So, whether you are building an integer n synthesizer or this kind of a fractional n synthesizer, you have got spurious frequencies and these spurious frequencies are precisely at the same frequencies as in both cases, right. Spectrum will look the same, spectrum will look exactly the same, except for the fact that in the fractional n the spurious frequencies will be larger, because why will the spurious frequencies be larger? Because they are within the loop. Okay. So, let us do a head on comparison of the two techniques that we have learnt so far. Integer n simple, fractional n complicated. It is more difficult to understand what is going on. Next, integer n slow, it is very slow. Fractional n can be made fast. Okay. Slow in the sense it has very slow settling time. The settling time is really inversely proportional to the loop bandwidth. The larger the loop bandwidth, faster it is going to be, lower the settling time. Next, what else? So, the integer n, I say that it has poor phase noise, fractional n has better phase noise. Why did I say such a thing? Because of low loop bandwidth. Integer n has a lower loop bandwidth, which means that it can mimic the reference over a lower bandwidth. Fractional n has more loop bandwidth. So, the VCO phase noise requirements are less stringent. So, I am just writing it as a harder VCO and an easier VCO, because it has better phase noise. Right. Then so, for the integer n, the spurs are cut out by the low bandwidth loop, whereas for the fractional n synthesis technique, the spurs pass through the filter, through the loop. Right. Now, these spurs happen to be precisely at the channel raster frequencies, which is very annoying to the base station. Why? Because these are the next channels where other users are going to be. You are transmitting signals at other channels as well. You are creating a lot of interference. So, as a result, this is extremely annoying as far as the total RF environment is concerned, right. So, therefore, we have a problem. Now, one more thought. Where did the spurs come from in the integer n case? In the integer n case, the spurs came from gate delay and mismatch between in the charge pump, in the two current sources in the charge pump. Where did the spurs come from in the fractional n synthesizer? Did it come from mismatches? No, it did not come from mismatches. It came systematically. Take a look at that, right. It came systematically. The way I divided my output frequency to compare it with the reference frequency, that very technique introduced equal and opposite up and down pulses of certain durations, remember, right. That is how we did it. So, that is where the spurs came from. So, the spurs in the fractional n are systematic. They have nothing to do with mismatches, they have nothing to do with gate delays, etc., etc. They are systematic. Okay. which of course means that these spurs are once again going to be much larger. Then the integer n case. In the integer n case, the spurs were tiny. I could lower mismatches to 0.1%, right. I could improve my, I could build faster gates, etc., etc. I could try to do a lot of things to get rid of the spurs in the integer n case. In the fractional n case, the spurs are systematic. They are going to be there. They are not because of any non-idealities in your circuit. It is the very technique that is introducing these spurious frequencies. All right. So, therefore, we need to seriously think about what can be a better way to do this division by n and n plus 1. So, you see over here for the fractional n, I like the fractional n because it is fast, it has better phase noise, I can make an easier voltage controlled oscillator. These are the reasons I like it, okay? And there is nothing that you can do in the integer n circuit to improve these. You can't do anything to improve these things, it is just not possible. You have to have the loop bandwidth 1/10 of the channel raster. So, what can I do to the fractional n to get rid of these spurs? These spurs seem to be very serious in this fractional n synthesis. They are very serious. First of all, they pass through the loop filter. Secondly, they are much larger because they are systematic. So, what can I do? So, once again, rethink and revisit. All right. What was my strategy to do this division? This division seems to be the basic stumbling block, because the division is creating the spurs, right, and I need to be able to divide by a fraction. If I just keep dividing by integers, it is not enough as far as loop bandwidth is concerned. So, I am calling this f out by k, it is in terms of frequency. Okay. So, this was our strategy, right. I was dividing by n or I was dividing by n plus 1. To do a division by 90.1, let us say I wanted to divide by 90.1, right. To do a division by 90.1, what we did was we chose n to be equal to 90, we chose a plus b equal to 10 and we chose b equal to 1. Right. This was how we managed to divide by 90.1. So, f out will be 90.1 times the reference frequency. Reference frequency is 10 megahertz. So, f out will be 901 megahertz. This was the strategy that we had. Okay. Now, you have to control over here digitally, but of course, when you are going to divide by n, when you are going to divide by n plus 1. And what are these a and b? So, for A times n cycles, A in our case is 9 and n is 90. So, what I am saying is for 810 cycles divide by n, and for the remaining 91 cycles, is it 91? Yeah, B is 1, n plus 1 is 91. So, for 810 cycles, it is going to divide by n, and for 91 cycles, it is going to divide by n plus 1. Okay. So, this particular logic circuit is clocked by this, and there is a counter over here that is going to count till 901, right, and out of this 901, it is going to say 810 times, let us count by n, and 91 times, let us divide by n plus 1. Okay. So, this is basically the thought process. What can I change over here to remove the periodicity? There is a periodicity over here, right. Every 901 cycles, it takes 901 cycles, every 901 cycles, out of that 810 it is asking to divide by n, 91 it is asking to divide by n plus 1. The output is always the same every 901 cycles, which means that the entire thing is periodic with a period which is 901 times the reference, I am sorry, 901 times the period of the output clock, which is the channel raster once again. So, we have to somehow break this periodicity. We can't let it be so periodic. What do I do? What do you think? What can be done? What can possibly be done over here? Now, think a little bit. Do you think this is some sort of an pulse width modulation? Do you see this as some kind of a pulse width modulated signal? This one. So, that particular signal over there is 1 or 0. If it is 1, you divide by n plus 1, if it is 0, you divide by n, that is the idea as far as the divider is concerned. Now, that particular signal is some sort of a pulse width modulated signal. You are modulating the width of the pulse. If you wanted 90.2, right, if you wanted 90.2, then you would do n equal to 90, a plus b equal to 10, b equal to 2, a equal to 9. This is what you would do, a equal to 8, I am sorry, which means 8 times 90 is 720 cycles. You would divide by n, and 182 cycles you would divide by n plus 1. So, that is how you would get a division by 90.2. Okay. So, the width of the pulse is kind of telling you what this division is going to be. If you were to divide by 90.3, the width of the pulse would be 630 to 273. Okay. The duty cycle of the pulse is going to increase. So, here the duty cycle was, if I wanted to divide exactly by 90, duty cycle is 0. Here the duty cycle is 10%, here the duty cycle is 20%, here the duty cycle is 30%, 90.3 duty cycle is 30%, 90.4 you expect a duty cycle of 40%, 90.5 50% and so on. 90.9 you will have a duty cycle of 90%, 91 you can do a duty cycle of 100% or you can change n and make the duty cycle 0%. Right. So, this is the plan, and as a result this particular signal over here is a pulse width modulated signal. Are there better ways to get this pulse width modulation? You are getting a pulse width modulated signal by counting clock cycles. You are counting cycles of f out and you are saying for this many cycles I will have a 1 over there, for this many cycles I will have 0 over there, and that is your pulse width modulated signal. Is there any other way to make a pulse width modulated signal? So, you are converting this number, this fraction that you want, to a pulse width modulated signal. How else can you create a pulse width modulated signal? Any other popular examples? Think about A to D converters. Ooh, where did A to D converters come here from? There is an A to D converter here. You are converting a floating point number, a fraction, into a 1-0 signal. You are converting a fraction 0.1, 0.2, 0.3, this kind of a number into a duty cycle of a 1-0 signal. How else could you do this? Sigma delta modulation or delta sigma modulation, whatever you want to call it. Are you familiar with delta sigma modulation? So, the thought is that you want to randomize this pulse width modulated signal, this pulse width modulated signal over here. You do not want it to be so deterministic, you want to create some randomness over there and you want to break the period at the output. You do not want that, you do not want the period of 1 megahertz. The period happens to be exactly equal to the channel raster, right, frequency. That is not good, that is exactly what you want to break. Now, we are going to go back, this is, we are lifting material from possibly a different course, analog to digital conversion. And we are going to take a brief look at what a sigma delta modulator does, very brief look. So, let us keep this on standby over here, pause over here, let us briefly study sigma delta modulation and then we will get back. Now, I will briefly study, I will only very briefly study this, right. It is your job to go back, probably look up the appropriate course or look up a book. Okay. There are books written about sigma delta modulators, or read some good reference papers. I can give you some good reference material, primer basic reference material as far as sigma delta conversion is concerned. So, that is going to be available with the references for this particular module, but that is your responsibility. I will only very briefly discuss the basics of sigma delta modulation. All right. So, sigma delta modulation is an analog to digital conversion technique. It is very popular, it is very robust, and why it is very robust is because of the use of feedback. Okay. So, we have used feedback in phase lock loops, we know something about feedback, right. So, this is how your feedback system looks like. Control system, this is how it looks like. I am going to call the input as x of t, actually let us call it x of n, let us make it a discrete time system, although there is no reason to make it discrete time. Let us call it x. Okay. It could be a discrete time system, it could be a continuous time system, that is your business completely. This is a feedback control system, and a sigma delta modulator is just another feedback control system. The plant that I am talking about over here is an A to D converter, it is a coarse A to D converter. Okay. The coarsest A to D converter that you can possibly think of is a 1 bit A to D converter. It is usually quite popular to put a 1 bit A to D converter as the plant over here. Okay. Why 1 bit? Because 1 bit A to D converter is trivial, it is extremely easy to build a 1 bit A to D converter, that is why. Okay. So, this is typically what people do. You can put a multi-bit A to D converter, lot of people like putting multi-bit 2 or 3 bit A to D converters or even 4 bit A to D converters as the plant. As far as we are concerned, it is just some A to D converter. Now, an A to D converter, unfortunately, unlike plants, an A to D converter introduces quantization noise. This is something unfortunate. So, I am going to model this system. This is just a model, it is not okay. So, this is how I am going to model the plant. The plant is something which introduces quantization noise. Now, you are going to come back to me and say that x is an analog signal, this error is an analog signal. Okay. This is the controller or the loop filter, whatever you want to say, that is an analog signal. Output of the A to D converter is digital. How can you convert, how can you subtract a digital signal from an analog signal? Well, yes, there has got to be a DAC over here, some sort of a D to A converter over here is necessary. If you are talking about 1 bit A to D conversion, then this D to A converter is trivial, there is nothing, in fact it is a wire, right, 1 bit signal, it's either VDD or it's 0, right. If you convert it to digital, I am sorry, if you convert it to analog, you again get back VDD and 0. So, it is okay. The DAC is a wire as far as a 1 bit A to D converter is concerned. If you want to make it a multi-bit A to D converter as the plant, then the DAC will have to be there. You will have to worry about the D to A conversion as well. All right. So, in our system, in any case, this D to A converter is not something that is going to add any noise. An ideal D to A converter, the model for an ideal D to A converter is a straight line, is a wire. That is the model for an ideal D to A converter. The input is so much, the output is going to be the same quantity, just that it is an analog voltage now. Okay. So, this is the model for our system. Okay. I have added some quantization noise here. This is the unfortunate part, and you are trying to make a controller to fix this problem. Now, suppose I restrict my X to be a low pass signal. So, this is the biggest thing about the sigma delta modulator, that I am going to restrict X to be a low pass signal. In that case, if I have, let us say, some sort of an integration over here, let us put one integrator over there, you can put 2, 3, as many as you like, let us start with 1. So, let us say the controller is an integral controller, all right. X is a low pass signal, let us say X is a constant signal. In that case, if the average E is not equal to 0, then the voltage over here is going to build up, which means that it can't happen, right. The average error has got to be equal to 0, right. If the average error is equal to 0, that means that the average of the output is equal to X. Is this understood? The average of the output is equal to X. I am not saying what are the dynamics of the output, I am just saying that the average of the output is equal to X. So, if I look at the spectrum of the output, at DC I will see X, at other frequencies I will see other junk, but I already know that my signal is a low pass signal. I already know that my signal is a DC, let us say. So, from this information, from this output, I can put my low pass filter and I can extract out the average quantity digitally. Is this okay? All right, let us think a little more. Let us say this loop filter is an integrator. Okay. Let us say that the property of the integrator, instead of putting an integral over here, let us say it is called H. H is either the Z transform or the Laplace transform of the impulse response of that loop filter. Now, whether you are using Z transforms or Laplace transforms, all depends on whether you are working with a discrete time system or a continuous time system. So, suit yourself. Let us say that is equal to H, the loop filter is equal to H. In that case, the transform of the output, that is Y, will be equal to X times h by 1 plus h forward gain divided by 1 minus the loop gain. Loop gain is equal to minus h plus q, that is the noise you have added, the quantization noise you have added, times 1 by 1 plus h. Forward gain is 1 and loop gain is minus h. So, this is the characteristics of y. Now, if h is such that at low frequencies it is infinitely large and at high frequencies it is 0. Right? That is an integrator for you. At low frequencies it is infinitely large, at DC it is infinitely large, at high frequencies it is equal to 0. So, then y at low frequencies is going to be x times infinity by 1 plus infinity. So, x plus q times 1 by 1 plus infinity, that is 0. Okay. And at y at high frequencies x times 0 by 1 plus 0. So, that is 0 plus q times 1 by 1 plus 0, that is 1. Very interesting. So, you added quantization noise and this quantization noise is kind of shaped in the frequency domain and is pushed towards high frequencies, whereas at the low frequencies you are stuck with the signal. It is wonderful, right. So, this is the idea of the sigma delta converter, where this name is coming from. There is, this is some sort of an integrator, which means you are doing some sort of addition sigma, okay. And you have got a subtraction over here. So, that is the delta. Now, some people call it delta sigma because the subtraction happens before the integration and so on. It really does not matter what it is called. The heart of it, it is a feedback control system. Okay. Now, you can build more and more intelligent transfer functions H to do better and better jobs. You can do first order H, you can do second order H, you can have a third order H, then you can have some zeros in H, etc., and you can do fancy stuff. And as far as I am concerned, as far as this particular lecture is concerned, all of this is irrelevant. What is relevant, let us come to that, is the dynamics of this. So, if you look at this output spectrum, now let us put a sampling frequency over there and let us say it is a discrete time system, all right. So, this is your Fs by 2. So, suppose it is a discrete time system. In our case, we have a discrete time system, right. So, the restriction for the sigma delta or delta sigma converter is that the input is a low frequency signal. It is not changing as fast as the sampling rate. That is the basic restriction. In fact, it is changing much slower than the sampling rate. What you are going to see is that because the loop filter passes the signal and cuts out the noise, the output of the sigma delta modulator will look like this. So, if you plot this in the log scale, if you plot x axis in log scale, then you will see a certain slope, and that slope happens is going to be equal to 20 times n, n is the order of the transfer function. Okay. So, we are going to stop here, and in the next lecture we are going to try to use this sigma delta to our advantage.